Hi, thank you for that nice introduction. At least I'm assuming someone introduced me. I don't know, this is a video. Anyway, I'm John Crum from Microsoft Research, and I'm going to talk about this paper called Brownian Bridge Interpolation for Human Mobility. This paper has to do with location trajectories for people. Often there is a long gap between measured locations in trajectories, and these long gaps may be due to battery savings on the phone, location privacy, whatever settings the user put in, or GPS dropout zones. But we often want to reason about what was going on in between the 2 points. For instance, we might want to know the probability of a person visiting a certain place, probability over what routes they might have taken, or we might want to compare this trajectory to another trajectory. One way to do that is with the Brownian bridge, which gives a probability distribution of where the person was between the 2 measured points. Here's a picture of a Brownian bridge. We see these big spikes at the actual measured locations, which are here and here. But this gives a probability distribution over where the person was when they were going between the 2 points. We all know what Brownian motion looks like. Here's an animation of it up here. In 1D, here's a picture of Brownian motion. Time is across the horizontal axis. The x-coordinate is along the vertical axis. The x-coordinate starts off as 0, and the location in x gets more and more uncertain as time goes on. Every slice in time here, the location is represented by a Gaussian distribution whose variance grows linearly as a function of time. A Brownian bridge, on the other hand, is a little bit different because we know the endpoint. So we're reasoning about where the person was in between the 2 measured endpoints. But there are still Gaussian distributions that represent the uncertainty of the location as a function of time. It's just the uncertainty goes down to 0 at the end. The Brownian bridge motion model has been used a lot in the animal tracking literature, where an animal has a radio collar that just emits a location measurement very infrequently, and researchers want to reason about what the animal was doing in between location measurements, and the location measurements can be hours apart. This is probably the most famous paper that talks about using the Brownian bridge for analyzing animal motion. It gives a lot of handy techniques for using the Brownian bridge for motion analysis in general, so I use some of these techniques in my work. But the Brownian bridge has also been used for analyzing the motion of people. Here are some papers where that's been done. And so the question that I wanted to answer is the Brownian bridge good for looking at the motion of people? The mathematics of the Brownian bridge are pretty simple. So here's an example. The person started here at time 0, ended up here at time 10. And what the Brownian bridge says is that at any time between points A and B, the distribution of locations of the person is just a 2D Gaussian distribution, where the mean of that Gaussian distribution is a function of time. This shows the mean here. And that mean is just a linear interpolation from the first point to the last point. The variance of that Gaussian distribution looks like this as a function of time. The variance is very low at the 2 endpoints where the location was measured and gets maximized at the midpoint in time. This is what the covariance matrix looks like. It's a diagonal covariance matrix where you can see variance as a function of time, which is just a parabola for the Brownian bridge. It's nice that there's only one parameter to fit for the Brownian bridge, which is the diffusion coefficient, which just says how high the variance gets at the midpoint. And that diffusion coefficient, sigma squared sub m, is computed from location data. In that famous paper on using the Brownian bridge for animal motion, they give the standard way of computing that diffusion coefficient, which is to do a numerical search for the maximum likelihood value. In the paper that I wrote that I'm talking about today, I derive a closed form version of that maximum likelihood estimate for the diffusion coefficient, just a simple equation right here. So that means that you don't have to do that numerical search anymore. You can just compute it outright with a closed form solution. So the advantages of using a Brownian bridge are that it fills the gap in spatial temporal trajectories. It represents uncertainty of interpolation, which is what we want because we don't know where the person was. The results seem kind of reasonable when you look at them. It's a simple to fit model. There's one parameter, especially now that there's a closed form solution for that diffusion coefficient. And it's been used frequently in the animal tracking literature. Of course, the Brownian bridge is not the only way to represent the uncertainty between 2 points. You could use a kernel density estimator, a Kalman filter, a particle filter, a Markov process, which has been used in our research area before, or a Gaussian process, which Kian talked about in the talk right before mine. So the real question is the Brownian bridge accurate for human mobility? Well, you can do some statistical tests to figure out whether or not it is. So I got a bunch of data from SafeGraph, which is a data aggregator and broker that gathers and sells cell phone location data. I looked at the first 3 days of November in 2020, looked at people that had between 3 points and 100 points, and that were in this lat-long rectangle. That amounted to 12 million distinct users and 314 million latitude-longitude points. The first test I did is looking at the Brownian bridge's prediction for the mean of the location of the person in between measured points. So remember, the mean is just a linear interpolation between the first point and the last point. So it's a little bit of a weird statistical test here because the mean is a function of time, but it turns out you can make a test statistic that's the predicted mean minus the actual point. The expected value of that difference should be 0, so we're actually testing for 0 in this statistical test. And you can do a normal everyday t-test on this, where the null hypothesis is that the Brownian bridge mean prediction is true. And if you look at the data, you'll see that in almost all cases, the test fails to reject the null hypothesis, which supports the mean prediction of the Brownian bridge. So at least for that part of the Brownian bridge, it seems to hold for human location data. The other thing to test is the variance prediction of the Brownian bridge, or more generally, just testing the assumption that the Brownian bridge gives that the distribution is a Gaussian, that it's normal. So it's a little bit of a weird statistical test here too, because we have both the mean and the variance of this normal distribution are changing in time, but it turns out you can do a little bit of math and come up with a regular test statistic that works for an everyday test for normality. And that test is the Hotelling test. And it turns out that if you look at the data, and the null hypothesis here is the Brownian bridge normality prediction is true. But if you look at the data, that null hypothesis is not supported most of the time. So that means that the Brownian bridge prediction for the Gaussian distribution in between points is not necessarily true for human location data. And does this make sense? Well, kind of yes. If you took a bunch of trajectories with the same length in both space and time and laid them on top of each other and computed the mean of all those trajectories, you probably would come up with a straight line. So the mean prediction probably makes sense. But the variance prediction, the normality, probably doesn't make sense in real life because people don't move like this. They move with a little bit more intentionality. So the summary of this talk is that actual trajectory data is often sparsely sampled due to privacy and battery. We often need to infer location, speed, or visits between samples. The Brownian bridge is attractive for doing this interpolation. There's only one parameter to fit, and it preserves uncertainty. But it doesn't match human data very well, which seems like bad news, but actually it's a nice opportunity for our community to find something better. So thank you for listening.